Okay, so this is the part 2 of proving independence. I wanted to highlight a portion of this packet that you guys have, the inside cover. If you're following along on OneNote, it'd be here at page 2. It has all these formulas, and we've actually used a lot of these already. The top 4 uh, talk about how to calculate specific probabilities. So the probability of A or B, when they're not mutually exclusive, I add the two probabilities together and I subtract the intersection. The probability of A given B, that's when I find the probability inside the two-way table and divide by the probability of that specific column. Notice that when B is the condition, B is the denominator. When A is the condition, A is the denominator, but the joint probability stays consistent for the two of them. I didn't really emphasize these two formulas when I was solving these. I just did it using reasoning by pulling apart what I needed from the two-way table. Another thing we talked about was when two events were independent, I could use this product property to find the probability of two things occurring at the same time. Again, this is important to know that I can only use this property here if independent. When I'm trying to prove that these two events or that two events are independent, I can also use this product property, but I need to now kind of view it as a question mark over the equal sign and say, well, are these equal? And if they are, then write a sentence explaining it. Same thing for conditional. Notice that I have the conditional statement up here, but I have the conditional statement down here, and I'm saying, are these two things equal? If so, then they are independent. If not, then they're not independent. And same thing here. So again, the condition is what comes after the vertical line. If I remove it, then it shouldn't affect the probability. Again, if I remove the condition, it shouldn't affect the probability. So let's try a few more examples. So we have a two-way table, and it talks about enrollment in Sutherland High School and specific courses that students can take. So first question says, what is the probability that a student would take calculus? So this is not a conditional probability. This is just a total probability. So my denominator for this one is going to be 675. And of the 675 students, 90 take calculus. Part B, what is the probability that a 12th grader will take either pre-calc or calc? So this is our condition. So again, I could use that formula that we wrote down on the inside cover, or we could just say, if that's our condition, then that's our denominator. Our denominator is 220. Our numerator is now the overlapping region that covers the 12th graders and the other two. In this case, there's two because it's an or statement, but the other attributes we're looking at. So in this case, pre-calc or calc. So I'm adding these two together. And so that will be 161 out of 220. All right, part C, what is the probability that a student taking Algebra 2 is a 10th grader? So again, our condition is given as Algebra 2. So that'd be 213. And our probability we're looking for is of the Algebra 2 students with the probability it's 10th grader, and that would be 74 out of 213. So the question is, are grade level and course enrollment considered independent events? Justify your answer. A lot of open-endedness here because it just says grade level and course enrollment. So I can literally pick anything I want. So maybe I'll highlight just one of the two conditional probabilities here. In this case, I did part C here was a conditional probability. So this conditional probability in part C was the probability, the condition was Algebra 2. And then the actual event was 10th grader given that they're taking Algebra 2. So essentially, if I use the concept from before, we have this conditional probability. If these events are independent, the condition should not affect the probability. So I could take away the algebra 2 piece of this. So I've already calculated this, 74 out of 213, and we're questioning whether that's equal to, now the probability of being a 10th grader is 225 out of 675. So 225 out of 675. And we could convert these to decimals. When we do that, we get, for the fraction on the left, we get 0.347 dot, dot, dot. And clearly that is not equal to 0.3 repeating. So we would say not equal means not independent. And again, when we're proving independence, we have to write a sentence. So not independent because the probability, or maybe I'll just use probability notation, the probability of being a 10th grader does not equal the probability of being a 10th grader given that they were taking algebra 2. Again, very random for me to choose those two. I could have done a conditional probability with B, or I could have used any other course here to answer this question. So kind of a neat trick, though, that happens with two-way tables is a consistent proportionality. So you can see that what I did was I did a fraction of 74 out of 213, and if I trace my fingers across the margin or over to the margin, I get 225 out of 675. And that's kind of a trick that we could use to kind of figure out what fractions we're comparing. I also could have compared 0.3 out of 194 to this 225 out of 675, or 3 out of 90 to 225 out of 675, and used all of those comparisons of ratios to prove that these events are not independent. And so that might lead us to kind of understand what's happening in this next question. Determine if gender is independent of taking AP Psych. So again, if you want to pause the video to kind of take a look at it, see what you can figure out, I'm just going to go ahead and get started. In this example, we weren't given the totals, so I'm going to add the margins. So we can see that we have 98 students that are taking AP Psych. We have 245 that are not taking AP Psych. We have 168 that are male and 175 that are female. And so the interesting thing about when you fill this in, if you did it right, that adding the two rows together or adding the two columns together should give me the same total. So in this case, when I add, I get 343, whether I added the 168 and the 175 or the 98 and the 245, those combinations still add up to 343. So determine if gender is independent of taking AP Psych. So we could do the probability that a student is male given that they take Psych. And we'd say, all right, well, the probability that a student is male given that they take Psych is going to be this ratio here, 48 out of 98, because we said our condition was AP Psych. So we get 48. All right, let me change color, 48 out of 98. Or uh, maybe you could pause the video, or I'll give you maybe 5 seconds to think about what I would need to compare that to. So again, to prove independence, I need to take away the condition. So the condition was taking AP Psych. So we're going to now compare that to the probability that a student is a male at this school. And you could see that if I go across and end up at the margin, I am now comparing that fraction. And when I do so, 168 out of 343. Now, it might not be obvious how to compare those two fractions. So the nice thing is, depending on the calculator you're using and the settings you have, if I just type those fractions in, I automatically get them reduced to 24 out of 49 and 24 out of 49. And so that means that gender and taking AP Psych are independent for this group of juniors. Because the probability that a student is male given they take AP Psych equals the probability that a student is male. All right, last type of question, which maybe you could figure out based on what we've been doing. If I have a two-way table, and you could see, again, going back to the last one, all of these proportions should reduce to the same thing. So if I compare this proportion, that should be consistent. Or even more specifically, I don't even have to go to the totals necessarily. 48 out of 50 is the same as 120 compared to 125. Those ratios are consistent across the board. They all reduce to the same thing, right? This is a 24 to 25 ratio when I reduce it. Well, if I take 24 to 25 and I multiply that by 5, I get this. And if I take 24 to 25 and I multiply that by 7, I get this. So keeping that in mind, there's only one value then that would make this table here an independent table. So again, you could pause the video, but I'm just going to go ahead and get started. So we are comparing these two proportions. So 20 to 30 is equal to 50 over n. And I'm just going to go ahead and use the cross multiply rule portions. And so we get 20n is equal to 1,500. And so if we divide by 20, we get n is equal to 75. That is the only number that would have made this independent. All right, so hopefully that's enough. We'll continue with independence in different scenarios as well, but that should carry you to the point we need to at least be able to start the homework. All right, good luck.